Hello everyone, I'm Patricia Diego, probably a new postdoc at the Max Planck Institute for Astrophysics by the time you watch this recording, but all of the work I'm about to present was done while I was still a PhD student at the Instituto de Física de Cantabria. And what I wanted to show you is how the polarization of the cosmic microwave background gives us a tomographic view into the evolution of the axion field through the measurement of the birefringence angles from the epoch of recombination and reionization. As you know, a discovery channel for axion-like particles is to try to exploit their potential coupling to electromagnetism through a Chern-Simons interaction. This interaction makes the phase velocities of the left and right-handed elicited states of photons differ, producing a rotation of the plane of linear polarization clockwise in the sky that depends on the coupling constant between axions and photons and the time evolution of the axion field. And this rotation is what we usually know as cosmic birefringence, and I am sure that Mark Minkowski has already given you a very nice introduction to the topic during his talk. If you look here at the definition of the birefringence angle, once nature has fixed the value of the coupling, the only free parameter we have that we can play with is the value of the axion mass, which is going to determine the time evolution of the field. And for this talk, I want you to think of ultralight axions with masses roughly between 10 to the minus 32 to 10 to the minus 28 electron volts, which will give us an axion field that behaves like dark energy for a significant fraction of cosmic history. Within this mass range, we know that the transition between the constant axion field behaving like dark energy into the oscillating axion field behaving like dark matter must have happened at some point after photon decoupling, but before today, so that it falls right between the two periods in cosmic history where CMB polarization is generated. The majority of CMB photons are produced during the epoch of recombination, around redshift 1000, but we also have a small secondary injection of polarized CMB photons happening during the epoch of reionization, around redshift 10. And what's more, these photons generated during reionization tend to dominate the large angular scales of CMB anisotropies, or equivalently the low multiples of the angular power spectrum, while the photons produced during recombination dominate the small angular scales and the highest multiples of the spectra. In this way, if we study the birefringence rotations seen at the small and large angular scales, or high and low multiples of the power spectrum, then we can get a tomographic view into how the axion field has evolved between redshift 10 and 1000. And that's what I wanted to show you today. How can we measure these two birefringence angles? Within the mass range we're talking about, we expect the background evolution of the axion field to give us a constant isotropic birefringence rotation, making the spherical harmonic coefficients of the E and B mode CMB polarization we observe a rotation of the original CMB emission, so that the EV correlation between them is going to be a rotated version of the original EE and BB CMB power spectra. And in principle, we could also have here an intrinsic EV correlation to CMB radiation, but that is something that we can neglect in the standard model, where we do not consider any parity-violating physics outside the weak interaction, apart from the axion field we are trying to find, of course. So removing this EV correlation, and with some simple algebra, we can rewrite the observed EV correlation as being a rotation of the also observed EE and BB power spectra. And this very, very simple equation right here has been the base of the majority of methodologies applied in the past to measure cosmic birefringence. However, there is really no way of knowing whether this rotated EV that we have measured has a cosmological origin, or it was just produced by a miscalibration of the polarization angle of our instrument, because both effects produce isotropic rotations of the whole sky that are completely degenerate with each other. Meaning that if your instrument is miscalibrated by a small alpha angle, then the EB that you measure will give you alpha plus beta instead of just beta. And this is a major setback because it means that to measure isotropic cosmic birefringence, you need a very precise absolute calibration of instrumental polarization angles, which explains why previous attempts at measuring isotropic birefringence have been limited by the 0.5 to 1 degree uncertainty in the calibration of polarization angles that most calibration strategies have been able to achieve so far. If you are interested in recent developments of this front, James Cornelison will tell us about the new calibration source that the BISEC team has recently deployed. So please go watch his talk. And in this one, I will instead tell you about a different calibration strategy that has allowed us to bypass this limitation through the use of galactic foreground emission. The key idea behind our methodology is to try and exploit this time integral, because for axion fields that evolve slowly, then birefringence is essentially proportional to the propagation length of photons, and in that case, it is safe to assume that the birefringence experienced by galactic foreground photons that were emitted right next to us is going to be negligible when compared to that seen by the CMB photons that have been traveling all the way back from recombination. So if we add a galactic emission to the observed signal, we do not expect it to be significantly rotated by beta, but it cannot escape the alpha miscalibration of the detector. And when we calculate the EV correlation of the signal, we will get the same term as before, and two additional ones, an extra rotation of the CMB spectra, and this term that depends on the intrinsic EV correlation of galactic emission. And what this term is telling us is that there is no free lunch. If you want to relax your requirements on instrument calibration, then you, to instead self-calibrate against the signal you see in the sky, then you obviously need to understand very well what that signal looks like. And in particular, for the frequencies covered by CMB experiments, the main polarized emission from our galaxy consists on synchrotron and thermal dust radiation. For synchrotron, we do not have any evidence of any significant EV correlation, but for dust, we know that the misalignment between dust filaments and the galactic magnetic field produces TB and EV correlations. And in fact, positive dust EV correlation has already been detected in Planck data, and we have hints that there is also a positive dust EV correlation. If you want to know more about the details of dust physics and of these correlations, please go watch Susan Clark and Ari Zuckerman talks. And in this work here, we detected the impact that this dust EV correlation has on the measurement of birefringence. When we studied the birefringence and miscalibration angles that you can recover from the study of the small scales of the dust-dominated frequencies of the Planck data. And I want you here to look up two things. First of all, I want you to see how much calibrating against dust allowed us to reduce the error bar compared to previous analysis of Planck data that were limited by systematic uncertainties. And second, see how much our measurement of beta started to decrease as soon as we started to mask the regions of brightest dust emission. And this strong mass-dependent bias arises from the nature of the dust TB signal itself. As the global dust TB that you get over the whole sky depends a lot on how you are masking and averaging all of these local misalignments between the filaments and the magnetic field. And the mass dependence is especially important when you are moving close to the galactic center. And it ended up being more important than the miscalibration of the polarization angles and our own statistical uncertainty. So we definitely need very good dust model if we want to use this methodology to measure birefringence. So far, we have tried two independent approaches. First of them, using this relatively simple misalignment ansat, where we can predict the dust TB correlation from the measurement of the EE, TB, and TE dust power spectra, without having to enter too much into the complicated details of the dust physics. And the second approach is just to take dust TB from the dust templates that Bayesian component separation algorithms like Commander produce by fitting parametric models of one component modified black body to Planck data. As you can see here on the right, These two ways to model dust agree quite well, far from the galactic plane, converging roughly to a 0.3-degree birefringence angle, but they have some tensions at the center of the galaxy, which might just be telling us that one of the models, or both of them, are struggling to reproduce the very complex emission of dust at the center of the galaxy. And once dust has been correctly accounted for, this methodology has given us a very promising hint of an unknown birefringence angle coming from small-scale information, so the epoch of recombination, with the tightest constraint today being a birefringence angle of 0.34 plus minus 0.09 degrees, coming from a joint study of Planck and WMAP data done by Johannes Eskil and Ichiro Komatsu. This measurement has proven to be very robust against instrumental systematics and is now sitting at a 3.6 sigma significance, so things are starting to get interesting. And regarding the potential physical origin for the signal, as Johannes will tell you on his talk, the data right now seems to favor a frequency-independent birefringence rotation, which supports our hypothesis that it is produced by a Chern-Simons coupling to a pseudoscalar field. And now that we have all of this knowledge and expertise from the study of small-scale information, we can move on to the study of large angular scales and the measurement of the birefringence angle from reionization. But this time, we're going to try a different approach to optimize the analysis to the measurement of the birefringence from reionization. And the first difference is that since we have already calibrated instrumental polarization angles, we don't really need to include foregrounds into the analysis of the lowest multiples. We can just focus on the CMB signal. And to do that, we are going to fit and subtract templates of the synchrotron and thermal dust radiation and calculate the CMB, EE, EB, and BB power spectra from those clean maps. In particular, we're going to use Planck S-roll data and cross-correlate the 100 and 143 GHz frequency channels to reduce the effect of noise and systematics. And here on the right, you can see the CMB, EE, EB, and BB angular power spectra that we get following that prescription from multiples 2 to 10, which are the ones we are going to use for the analysis. And using this power spectra and the noise covariance metrics describing the data, we would then like to perform some Bayesian inference to sample over the model parameters and recover their posterior distributions. However, since we have excluded foregrounds and we are going to stop at a multiple of 10, we really have no constraining power over either the miscalibration angles or the birefringence from recombination. But don't worry, we can take all of the information we got from the analysis of the small-scale data and get that best fit result, introduce it here as a Gaussian prior to still be able to sample and marginalize over these parameters. And for the likelihood itself, we are going to use Momento, a semi-analytical likelihood approximation based on the principle of maximum entropy that has already been successfully applied to measure cosmological parameters like the optical depth and the tensor to scalar ratio from the lowest multiples of Planck. So you can see this as an extension of a tried and trusted methodology. And without further ado, here I am showing you our preliminary results on the first ever attempt at simultaneously measuring instrumental miscalibrations and the birefringence angle from the epoch of reionization, so far using only EE and BB information. Because although EB is the optimal channel for this type of study, it is also a harder beast to tame, and right now results are not robust enough for us to feel comfortable sharing them. As you can see here, we are finding a birefringence angle from reionization essentially compatible with 0 and an optical depth of 0.054, which is compatible with previous results that didn't include birefringence. And we are also recovering the expected degeneracy between these two parameters. Let me walk you through it. Our results are mainly driven by EE information, because that is the power spectrum that we measure with the highest signal to noise. And in EE, here you have the approximate effect that birefringence will have. It would be a cosine square of 2 times beta multiplied by the unrotated EE spectrum where tau controls the height of the reionization bump. So a large value of beta can be perfectly confused with a slightly lower than expected value of tau, making these two parameters anticorrelated. But since beta enters through a cosine square, you cannot really differentiate positive from negative angles, and instead of the perfect anticorrelation ellipse you would classically expect, you end up with this symmetric confidence contour. It is EB information, where beta enters through a sign, where we will be able to distinguish between positive and negative angles. And all in all, I'm quite happy with the 2.7 degree uncertainty that we get in determining beta from reionization. Of course, 2.7 degrees pales in comparison with the 0.09 degree uncertainty we had in the analysis of the small scale information, but it's actually quite impressive when you take into account that these 2.7 degrees are essentially coming from the first 5 multiples of a single cross spectrum, where birefringence is only a second order effect. And let's be honest, Planck data is still rather noisy at these scales. And on the other hand, the small scale analysis is fully exploiting the EV correlation across more than 1,000 multiples and using all of the possible cross correlations between 22 frequency bands. So 2.7 degrees is actually quite good. And just to sum up, CMB polarization offers a tomographic view into the evolution of the axion field through the measurement of the birefringence rotation at small and large angular scales. In recent years, we've found a very promising hint of a 0.3 birefringence angle from the epoch of recombination that is very robust against instrumental systematics, but sensitive to the dust EV correlation. So moving forward, we need to continue refining our dust models or alternatively improve our artificial calibration sources if we want to confirm the nature of this signal. Nevertheless, this 0.3 birefringence angle has been independently detected on WMAP data and on both high and low frequency instruments of Planck, of course to different levels of significance. But this gives us confidence that the signal cannot be entirely attributed to either foregrounds or systematics. And I have just shown you some preliminary results on the first ever attempt at simultaneously measuring instrumental miscalibrations and the birefringence angle from reionization. Right now, using only EE and BB information, but we are working towards including EB in the analysis. Well, at the moment, with Planck data and a 2.7 degree uncertainty, there's not much we can say about the underlying axion field. So please take this work as a demonstrator of what CMB information can do and a pathfinder setting the way for future analysis. Thank you.